Today, I want us to look at the rules for limits. And to be more specific, I want us to talk about 9 rules for limits. Right. I have to be honest about this. Other people, instructors, wanted to start with these rules before actually going to solving a 0 over 0 limit and also solving a number over a 0 limit. But of course, people choose different things for different reasons. For me, if you have noticed, we started the other way around. It's not personal or this way is better than the other or that one is better than the other. What is actually important about this whole thing is that if we went through all the other two, chances are very high, let me repeat it, if you already know how to deal with the 0 over 0 and a number over 0 limit, then you know how to deal with these 9 rules for limits. But of course, there are 9 of them. But you will notice that I can just summarize 8 of these rules in just one word or just one rule or one phrase. The 8 other rules are just saying, please plug in. That number that you are getting is actually your limit. That's what this lesson is all about. But we want to actually split it a little bit. You gain some little bit of theory and some other ways of actually looking at a limit. Let's start with the first one. The first one is, remember, this is a keynote. The 8 other rules are just saying to you, plug in the value you are getting is your limit. Let me just place a question mark there. Let's start with the first one here. The first rule is saying something that is very much interesting. That suppose that you have 2 functions, f of x and g of x. Those 2 functions are actually equal everywhere close to a. Let me just say here, when x is not equal to a, those 2 functions are actually equal. Then let me just say the limit. If I were to take the limit as x approaches a of f of x and the limit as x approaches a of g of x, this is what's supposed to happen. Take note that these 2 functions are actually equal everywhere except at that point. Going back to the meaning of what a limit is saying that pick a value so close to a, but we don't want that value to be a because at a the function might not even be defined. So we're looking for a value that is so close to a. But every time I am picking a value that is so close to a, I get equality. This function and that function are equal, because these 2 functions are only unequal at that point, but close to this point they are equal. So if that is the case, I pick a value so close and I plug it there. This function is supposed to be just equal to g of x. And also the same thing now, we just say the limit as x approaches a of f of x is supposed to be equal to that. But this is only going to actually happen provided that the limits. What I mean by these limits, I mean this limit exists and also that limit also exists, provided that the limits exist. Let's take an example, just one example, to see how this thing actually works. Suppose we are saying that I give you an example here. I'm just gonna call this as an example, and the example is saying to you, evaluate the limit as x approaches 1 of x squared minus 1 all over x minus a 1. Literally speaking here, if you were to evaluate this limit, the first thing that we usually say is very simple. We said that first plug in and see what you are getting. So if I'm plugging in a 1 here, 1 squared is 1, and then 1 minus 1 is 0. If I'm plugging in 1 here, I will get 1 minus 1, which means I will end up having 0 over 0. When I have a 0 over 0, there are 4 ways, but we only have done 2. The first one is factorize. The second one is rationalize. Here we can factorize. There is no need for rationalization. So this limit here as x approaches 1 of x squared minus 1 all over x minus 1 is supposed to be the same as the limit as x approaches 1 of x minus 1 and x plus a 1 all over x minus 1. X minus 1 and x minus 1, they cancel out, and now you end up having the limit as x approaches 1 of x plus a 1. Of course, if you are evaluating this, because now I'm going to pick that value that is so close to 1 but not 1, such that the calculator cannot pick the difference out, so I will end up saying that I end up having 1 plus 1, which is just a 2. Of course, this is one of the basic problems that we have. Now let's take a note here. I'm gonna surround this piece here. Now if you look at f of x, and my f of x, let's say, is x squared minus 1 all over x minus a 1, and then let's look at our g of x. Let's say our g of x now is this function here, which is x plus a 1. Now if you look at the domain of this function here, this function is defined everywhere except when x is equal to 1, because the denominator is going to be a 0. So we usually say that the domain of this function, x cannot be equal to a 1. But if you look into this function here, you can find out that this one is defined everywhere. So if, let's say, you factorize this function, you will end up having, because we factorize it here, you end up getting that, and when you're cancelling out, you end up getting that. So this f of x of ours is the same as x plus a 1, but x cannot be equal to 1, because if x is equal to 1, this part is going to be undefined. I mean, the denominator is going to give you a 0, so this whole thing is going to be undefined. Now what we are actually saying by this rule here is that it's okay as long as these two functions are defined everywhere except at that point. The limit of this function and the limit of that function is supposed to be the same. So if, let's say, you're looking at the limit of this function here, you will find out that its limit is equal to 2. Hence, when we are finding the limit of this whole thing, we factorize and end up getting this, which is equal to g of x everywhere else except at that point. The reason this function is not equal to that is because f is not defined when x is equal to 1, but this one, x is an element of real numbers, so it is defined everywhere. So when someone is saying this function and that function are not equal, it's because of the domain, because this one is not defined at that point. Why is it not defined? Because here, if I were to plug in this one, I will get a 0 in the denominator and it results to an undefined. So basically, this rule here is saying that you can manipulate this function to another function that is equivalent to it at all other points except at that point, and then find that limit. So that is what this rule is actually saying. Of course, do you need to know this rule? Yes, because that's the theory behind it. But how do you end up solving this limit? It's very straightforward. When you're plugging in here, you get a 0 over 0. When you're getting a 0 over 0, factorize. After factorizing, you plug it in. Once you plug in, that value that you're actually getting is your limit. But in this part here, we're just trying to actually explain the theory behind it, that actually this function here and that function are not equal at that point, but they are equal everywhere else, because this one is not defined there, that one is defined everywhere. Now let's look at the second rule. Before we say the second rule, this is what is needed. I'm gonna use the black again here. Suppose that C is a constant. So we have a constant here. This constant is a real number. It can be positive, it can be negative, it can be zero. It's just a constant. And the limits, so these limits here is going to be the limit as x approaches a of f of x, and the limit as x approaches a of g of x exists. What we actually mean by this is that as long as this is a constant and I know that this limit here can be evaluated to some value and this one here can be evaluated to some value, which means it exists, right? On both on the left and on the right, we're approaching the same value. That's what we mean by this, it exists. Right, then this is what's going to happen. We have our rule 2 here. If this one exists and that one exists, this is what we actually mean by rule 2. If you take the limit as x approaches a of f of x plus some g of x, then this limit here, you will get the same value as if you were to first take the limit as x approaches a of f of x, right? And then you add it with the limit as x approaches a of g of x. So you can either split this, take the limit of this first, take the limit of that, and then you add them. Then the answer you're supposed to get is the same. Literally speaking, what this thing is simply saying, try and plug in and see what you are actually getting here. And then let's take an example here so that you can actually see what I'm talking about here. If, let's say, we are actually having something interesting here, like let me think of an example here. Evaluate the limit as x approaches 0 of I have x plus e to the power x. I want you to evaluate this particular limit here. What this rule is saying is this. First, let f of x equal to x and your g of x to be equal to e to the power x, so that you have two functions. So if you look into this function and look into that function, what you end up seeing is that actually I can take the limit as x approaches 0 of f of x, which is just the same as the limit as x approaches 0 of x, and this is just supposed to be like this. If I were to find the limit, if I pick a value so close to 0 on the right and I plug it there such that the calculator cannot see the difference, here I can just get because this is a straight line, so a straight line that is passing through the origin, like a straight line like this. So as I keep going closer to 0, this function is getting closer and closer to 0, so this is supposed to be a 0. And if I look into the limit as x approaches 0 of e to the power x, I am actually supposed to end up getting because this exponential function is increasing throughout, so, and at every point, if I were to draw it, I just continue to draw it. So at that point there, where x is equal to 0, I know that this function on the right is approaching. Let me just draw it, maybe you will see something here. So let me just draw it here. So that function is supposed to keep growing like this, and at this point when x is equal to 0, this is a 1. So this is e to the power x. Now that I have e to the power x, this is 0. As I keep, if I pick a value on the right of this 0, just so close to 0, such that even the computer itself cannot pick it up, and I plug it here, it would be as if the calculator is not going to pick out the difference between that value, because that value is so close to 0, and then the calculator is not going to pick the difference between x equal to 0 and that point because it's so close. And then the calculator is just gonna say, that's just a 0, why not just plug in a 0, and then you end up having a positive number raised to 0 is going to be a 1. Now, what this rule is actually saying here, it is just saying that, this rule here, it is just saying that, this limit that we are trying to evaluate here is just supposed to be equal to 0 plus 1, which is 1. That's what this thing is saying. Like I said in the beginning of this lesson, I said that the limit as x approaches 0 of x plus e to the power x, the first thing you do, just plug in and see what you're getting. If I'm plugging in 0 here, I will end up having 0 plus e raised to 0, which is just equal to 0 plus 1, which is equal to 1. Of course, that is why we always start by just plugging in and see what we're actually getting here, because this rule, splitting it into two, sometimes it becomes so tedious than just plugging in. But you have to know the theory behind that. If you have two functions, you are adding them, you must know that you can just add their limits as long as the limits exist. That's what I want you to see. But the shortcut is, we've already done that. Just plug in and see what you're getting. Are you getting a number? Or are you getting a 0 over 0? If you are getting a 0 over 0, you know what to do. But if you are getting a number, that might be your limit. Think about it. Now we need to look at the third. The third is similar to the second one, because it's just saying that the limit as x approaches a of f of x minus g of x, this whole thing must actually be equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. So this is also another rule, which is just saying that you can just take the limit of this first and the limit of that first. As long as this limit and that limit exists, then this and that will always be equal. So what we are actually going to end up with here, we will end up saying, let's try and have an example here which says that evaluate the limit as x approaches 0. Let me say I have 5 to the power x minus e to the power x. Now, to find the limit of this, I can just say this limit is going to be the same as the limit as x approaches 0 of, I'm going to take this first one as a one function. I'm going to say that I have 5 to the power x minus the limit as x approaches 0, and I'm going to take this function here as another function, g of x. So I'm going to end up having e to the power x. And if you look into that, this function here, I can say that I can plug in there, or if I pick a value so close to 0 and I plug it in there, I can end up seeing that actually that is going to be 5 raised to 0 minus e raised to 0, and 5 raised to 0 is going to be 1 minus, and this one is also going to be 1, which is equal to 0. What is important here when you're solving these limits is simply this. Whenever you are picking a value so close to 0, I want you to notice that actually that value, because it's so close to 0, a calculator is not going to find out what that value is. So when I'm plugging in that value and then plugging in a calculator, the calculator is going to assume that, because it's going to round it off to 10 digits, because this calculator can only show you up to 10 digits. And then after that, it's gonna say, that's just close to 0, because within these digits that I can process, the number that you have at the end, I can't see it, so you end up having a 0 here. So we'll end up having a 0 minus e to the power 0, which is 1 minus 1, which is a 0. So that's what is simple this. Of course, one way you could have done, you could have just skipped this whole thing and plugged it in, because the first rule that we usually use is plug in and see what you're getting. So here we're getting a 0, that's the limit. But if you're getting a 0 over 0, then that's not your limit. And also if you're getting a number over 0, then there are processes to deal with those two cases. But this particular case of today, when you're plugging in, are you actually getting a value? If you are actually getting a finite number, that finite number is your limit. So that's the main goal of today's lesson. Let's go to the fourth one. The fourth one is simply saying that the limit as x approaches a of I have a constant times some function f of x. I can always take that constant in front of the limit and take the limit of that function and then multiply later. So first take the limit as x approaches a of f of x, and then multiply that by that constant. That will be your limit. Simple, but an example will be what is the limit as x approaches 1 of 10 log base 5 of x. Let's take a look into this. If you noticed when we're actually doing the exponential and the inverse of an exponential, which is a log function, I want you to take note of something here. That time we said that if this base here, the base that is here, whenever you have log base a of x, suppose I have this nice thing here. If this base here is, suppose this base here is between 0, so I have a between 0 and 1, right? It's not 0 and it's not 1, it's just in between. This logarithmic function is going to look something like this, right? But it's not going to touch the y-axis here. It's going to cut, and this point here is going to be a 1. And if this value here a is bigger than 1, so if we have a, this one is when a is this one is when 0 is less than a and a is less than 1. And if you have your a bigger than a 1, then this function is going to look nicely like this. So in this case here, I have a 5 is bigger than 1, so we're actually landing in this case where a is greater than 1. So we don't have this point here, so this one is not needed. I'm just giving you a quick recap so that you can remember a log function, that a log function always either look like this or it looks like that, depending on the value of a or the base. Now we have a 5, so it looks like this, right? Because 5 is bigger than a 1. Now if I were to look into this function here, let me multiply this by a 10. So if I'm multiplying this function by 10, I am actually stretching this function by a couple of units, right? And then this one is gonna go down. It's gonna go down like that. So I will end up having a function that is little bit it's still gonna pass here. It's going to be something like this. It's not that good, but not that bad either. Yeah, so it's going to look kind of like this. This was supposed to be a little bit smoother here, a little bit smoother, but it's going to pass through 1. This point is 1 because this one is shrinking. I mean, we were actually stretching by a couple of units and also stretching this by a couple of units. Now that we actually have this by 10, can you notice that actually this curve, as we're getting closer and closer to 1, so if I were to pick a value so close to 1, then the output is still somewhere, the output is still here at 0. So basically this limit using this diagram here is actually going to tell you that, basically speaking, this limit is just supposed to be equal to a 0. But now, looking into this in this rule here, this rule is just saying actually that the limit as x approaches 1 of 10 log 5 of x is the same as take this constant in front of the limit, and then as x approaches 1 of log base 5 of x. Then what is the limit of this function? We know that this function is actually defined everywhere from 0 all the way up. Because of that, when I'm picking a value close to 1, I know that the output would be 0, so it's going to be 10 times 0, which is just 0. That's what that rule is saying. Pull out the constant in front and then take the limit, and then as you actually go, you will be able to actually find out the limit. Of course, log base a of x is one of the basic functions. You should know what is happening close to 1. Just like when you are dealing with an exponential function, you should know what is happening close to x is equal to 0, where y is equal to 1. Those are one of the interesting points. Let's look at rule number 5. But if you take a note here, if I just were to plug in here log base 5, here's log base 5, and then I just plug in a 0 here, the answer I'm getting is 0. No, not 0, 1. Because we're plugging in this one here, so I'm plugging in a 1, and I multiply this whole thing by 10. I think that's why I keep telling you the same thing. First plug in and see what you're getting. If you are getting a value like this, that's your limit. But if it happens that you're getting a 0 over 0 or a number over 0, then that's when you have to apply another methods. This is basically what is happening. You just plug in, just like the other two rules up, we're just plugging in. So today's lesson is all about, can you plug in the value? Now, the limit as x approaches a of f of x times g of x. This limit is the same as the limit as x approaches a of f of x times the limit as x approaches a of g of x, which means that as long as this limit exists and that limit exists, you can take this limit first and then take this limit second, and then you multiply them, you will be sorted. Now let's take another example here. The question is, evaluate the limit as x approaches 0 of x squared minus 1 times pi to the power x. To solve this whole thing, all you need to do here, realize that there is multiplication there and treat this one thing as a separate function, and this one here is a separate function. What is good about this thing, you know this function because this is a constant raised to an independent variable, and this constant here is pi, so this whole thing is this part is going to be an exponential function. Looking into this part here, you can see that basically speaking, this is a quadratic, and you know how to plot a quadratic, you know the information about quadratic, so you split this as one function, that one as also another function. Just because this is a quadratic and this is an exponential, it doesn't mean this whole thing is an exponential function. In matter of fact, this one falls under transcendental functions, and this piece here falls under polynomial. So you have this nice mix here, because this one is not a polynomial, only this part is a polynomial. So this whole thing is going to end up being a transcendental function, not an algebraic function. But we are not there, we dealt with that stuff. So now what we only care about is evaluating this limit. So this limit is going to be the limit as x approaches 0 of x squared minus 1 times the limit as x approaches 0 of pi raised to x. First thing is, let's plug in and see what we are getting. If we are plugging in a 0 here, we end up having 0 squared minus 1. And then for plugging in a 0 here, we end up having pi raised to 0. And what is good about this whole thing is that 0 squared is 0, minus 1 is going to be a minus 1 times, I have this thing here, a number, this pi is positive, you raise it to 0, you end up getting a 1. So this whole thing is going to be just a minus 1. Another thing that you would have done, you should have just plugged here in, and then you ended up finding your values without writing that. But the most important thing now, you can recognize that you end up having two functions being multiplied together, and that's what is important. Of course, most of the time when you're dealing with limits, you don't have time, so the first thing you usually do, you plug in. And then if you are getting a value, that's your limit. If you are getting a 0 over 0, you deal with it. If you are getting a number over 0, you deal with that. And of course, we'll deal with other rules later. When you're actually not getting a 0 over 0, it's either getting 0 over infinity, or you're getting infinite over infinity, or you're getting 0 times infinity, or infinite times infinite. Those things we'll deal with them at a later stage. For now, if you are getting a finite number, just know that that is nicely your limit. Let's go to rule number 6. Rule number 6 is saying, if let's say you have a limit as x approaches some a of f of x divided by g of x, right? Of course, here we are assuming that when I'm plugging in a here, I am not getting a 0. Because if I'm getting a 0, I already know that if this one is a 0, this whole thing is either is falling under 0 over 0 or a number over 0. Then we already know how to deal with it. So it cannot be boxed in here. So this one is going to be the same as the limit as f of x as x approaches a, all over the limit as x approaches a of g of x. That's what is important here. Also, given that the limit, if the limit as x approaches a of g of x is not equal to 0, because if this limit is equal to 0, then you have to think about this again, because this one might fall under 0 over 0 or a number over 0. In that particular case, we know how to deal with this particular that particular problem. So if there is not enough information given about g of x, then this particular problem relating to this can either be not solved. Some people usually just assume that the limit does not exist, but that's not always the case, because sometimes it can exist and becomes either positive infinity, all right, negative infinity, because either the function is approaching on both sides to positive infinity or on negative infinity. Of course, again, some people prefer to say positive infinity is undefined, but that's really not what I want to say, because we still have limits, infinite limits, so we cannot really say it's undefined. We just can say that we don't have enough information if we only know that the limit of this is equal to a 0, and we know the limit of that. We can't really say that we are actually having this undefined thing. Right, let's take an example. Let's take an example. Maybe this is going to make a lot of sense. The first example is evaluate the limit as x approaches 0 of 3 to the power x all over x squared minus a 1. So for this thing here, if I were to plug in here a 0, I will end up getting a number, right, which is 3 raised to 0, which is going to be 1. And if I were to plug in 0 here, I will end up getting 0 squared minus 1, which is minus 1. So I don't have a problem in the denominator, which means this whole thing is just supposed to be equal to the limit as x approaches 0 of 3 to the power x all over the limit as x approaches 0 of x squared minus 1, which is equal to, if I were to plug in here, I will end up getting 3 to the power 0, and here 0 squared minus a 1, which is going to be the same as just 1 in the numerator. In the denominator, I will end up having minus 1. The answer is minus 1. So basically here, even if I were to just plug in, then I would end up having that. So first rule, plug in and see what you are getting. If you are getting a value, this nice value, that is actually your limit. If you're not getting it, you might be falling on something else that is also interesting for you to actually investigate. Another example will be evaluate. I want us to look now at the limit as x approaches 0 of 3 to the power x divided by I'm actually doing this the other way around. So here I am actually having x squared divided by 3 to the power x. So if I am plugging in here, I am plugging in a 0 here, I will end up having 0 squared, which is 0. And then if I'm plugging here a 0 in the denominator, I will end up getting 3 to the power 0, which is 1. And I have a 0 over 1. That's not a problem because in the numerator, I am allowed to have a 0. The issue is in the denominator. If I have a 0 in the denominator, there is a special way to deal with that. Otherwise, this is just supposed to be the same as the limit as x approaches 0 of x squared divided by the limit as x approaches 0 of 3 to the power x. Of course, if I were to just plug it in here, I will get a 0 divided by, if I were to plug it in here, I will end up having 3 to the power 0, which is the same as just 1. So the answer here is 0. So this limit here is just equal to a 0. Now, let us look into this thing here, right? Suppose now I want you to evaluate the limit as x approaches 0 of 3 to the power x all over x squared. How do you deal with that? Now, the first thing that you do, if you were to plug in here, you will end up having 3 to the power 0, which is 1. But if you were to plug in here, what you would end up with here, you would end up with 0 in the denominator. But now, if you are having a 0 in the denominator, then we cannot apply rule number 6. So this rule can only be applied if the denominator is not equal to a 0. Right. Now, what do we do in that case? Take note that every time you have this you have two functions. One is in the numerator and one is in the denominator here. So I have 3 to the power x, but this function here, this whole function, is just the same as 1 over x squared. I'm going to stop there for a moment and then go back to these rules here. If rule 6, which is division, cannot actually work, then what you need to try is try and manipulate your function so that you end up having multiplication of two functions. And I say it again, if your division here is actually not working nice for you, then split these two functions. Let me rewrite this somewhere here. Take note that whenever you have f of x divided by g of x, this is the same as having f of x times 1 over g of x. So instead of having this division, just try and have multiplication by manipulating your function so that this becomes one function and that becomes one function, 1 over g of x. Now, let's go back and try and do that. In other words, we want to use rule number 5. So in this particular case here, trying to use rule number 5 here is just going to say to us the limit as x approaches 0 of this whole thing is going to be just the limit as x approaches 0 of 3 to the power x times the limit as x approaches 0 of 1 over x squared. That now is something that we need to actually talk about, because now I've decided to split this into two functions that are multiplied instead of dividing, because according to the rule of division we cannot divide here, but multiplication is helping us to deal with this particular case. Now I know how to deal with this one because it is defined everywhere. So let me first deal with that. The limit as x approaches 0 of 3 to the power x is going to be 3 to the power 0 times the limit as x approaches 0 of 1 over x squared. And this whole thing here, of course, is going to be 1. So a number which is positive raised to 0 is going to give you a 1. So this is just the same as the limit as x approaches 0 of 1 over x squared. Now, if I were to plug in here, this x is equal to 0 in this function, I will end up getting a number over a 0. So there is only one way to deal with a number over 0, and that is actually saying just draw a Cartesian plane. Mine is bad, but not that bad, we can work with it. And then after drawing the Cartesian plane, you go to x is equal to this value, x is equal to 0, and have your vertical asymptote there. Once you have a vertical asymptote at x is equal to that value, pick a value just on the right of 0, and a value just on the right of 0, you plug it there. So if I'm plugging a value on the right of 0, a positive value, and I square it, I'll get a positive value. A positive 1 divided by a positive value, I'm gonna get a positive. Once I have a positive, which means the function as I'm getting closer to 0 is going all the way up to positive infinity. In other words, the limit as x approaches 0 on the right of 1 over x squared is just equal to positive infinity. I pick a value on the left of 0. If I pick a value just on the left of 0, it's going to be negative, of course. I plug it here and I square it up. Of course, squaring a negative, I get a positive. And then a positive 1 divided by a positive value, I get a positive, which means the function on the left of 0 is actually getting closer and closer to the y-axis, but it's not going to touch it, but it keeps increasing unboundedly. Which means now the limit as x approaches 0 on the left of 1 over x squared is equal to positive infinity. So this limit here, because the left hand limit and the right hand limit both are actually equal to positive infinity. So this limit exists, it is equal to positive infinity, or this limit here is actually equal to positive infinity. Instead of going all this way out, take a note that you could have just evaluated this limit from here, because if you're plugging a 0, you will get a number over 0. You know how to deal with that. This is the way. You could have just went from here to this point without going through these steps. These steps were just illustrating them that actually there are rules that we use or we have been using. They are kind of a little bit hidden, but these rules are the one that we have been using to get up to this far. So rule number 6 is just saying that the limit of a fraction is just equal to the limits of is equal to the fraction of the limits of both the functions. Let's look at rule number 7. Rule number 7 is saying something very interesting now, that if I have a limit as x approaches a of some function f of x raised to some exponent n or some power n is just equal to, I can first take the limit and then give it the power. So I have to first take the limit as x approaches a of f of x, and then at a later stage I take the power, as long as this one is just a positive integer. So that's what is important about this n. If this n is a negative integer, you know that whenever I have a raised to minus n, this is always going to be the same as 1 over a to the power n. And once you have something of this kind, you use rule number 6 of these limits to deal with a fraction. But for now, let's just assume we have a nice thing which is positive here. Example will be, say e.g., find the limit as x approaches 1 of, I'm going to say here, I have x squared minus 1 raised to 10. How do we evaluate this limit? This rule is just saying that because this number here is positive, what is nice is just like, okay, let's take the limit first as x approaches 1 of x squared minus 1 raised to 10. Of course, what is the limit of this? As I'm getting closer and closer to 1, of course, I just plug in 1. 1 squared is 1. 1 minus 1 is 0. So I end up having 0 to the power 10, which is just a 0. Another way will be the limit as x approaches 0. No, let me not use 0 now. Let me just use random 5. And then here, I want us to look at when the function that is actually going to be defined. Let me just say we have e raised to power x plus some x, all raised to a maybe 100. Because we cannot expand this and then take the limit is saying that as long as I can find the limit of the inside, so I'm going to end up taking the limit as x approaches 5 of e to the power x plus x, and then later I give it a power 100. And then of course this whole thing is going to say that inside here I can take the limit of this and the limit of that, add them. Of course, you can just do that or take the shortcut of saying this is going to be e to the power 5 plus 5 and then all raised to 100. And then you can find your approximation here, because I don't think you can have a value of this and have a nice number of these two. I think that's enough. So that's how you end up dealing with this. Once you have an exponent there, first take the limit inside and then you give it a power there. Let's go to rule number 8 and then we'll go to the last one, which is 9. If I have the nth root of this function and I want to find the limit of that as x approaches a of this nice function, this one is not properly written. Let me try and rewrite it. The limit as x approaches a of f of x, taking the nth root of that, this is supposed to be the same as, I'm going to take the limit first of what is inside as x approaches a of f of x, and then later I'm going to take the nth root. Right. And of course here, we always say that where n is a positive integer, right? N is a positive integer. Now, if let's say n is even, suppose n now is even, so it's either 2, 4, 6, 8, and so forth. We know that the square root is only defined when what is inside is positive, or the fourth root if what is inside is positive. So if n is positive, we assume in this rule that the limit as x approaches a of f of x is greater or equal to a 0. So that's what is important here. In other words, you cannot use this rule if when you're taking the limit you'll get a negative number inside, because we won't be able to take the root. Okay, let me clarify something here. But if this n here is odd, then whether this limit is positive or negative, we don't give a damn, because the nth root will be easy. For instance, if you have the cube root of -1, you know that this can be done and you end up having a -1. The fifth root of -1, you know this can be taken. The seventh root, you know that this can be taken. So the issue that we have is when n is odd. When n is 2, 4, 6, or 8, or 10, then we want what is inside to be positive. Otherwise, we can't use this rule here. So if you look into this here, this limit, what is actually saying here is that I can just plug in a 1 here and see what I'm getting, and then raise it to the exponent 10. So I can just plug in. That's what 7 is saying. 8, as long as I know I'm not going to get a negative inside and the root is even, then I can always plug in. So all these rules, okay, are the above rules except rule number 1. All of them are just saying, if possible, just plug in. Unless now you are dealing with a piecewise function. When you are dealing with a piecewise function, you have to be very careful. But if you have a one function and you can plug in, then you are sorted. That value that you are getting is actually your limit. But if you have a piecewise function, then you have to really evaluate around each of the points whereby you are having a point of discontinuity. We will deal with this piecewise function when you are dealing with continuity. Don't worry about it. In this particular case, we are taking about a function that is actually written like f of x is just equal to this. We don't have those conditions if x is less than that or if x is greater than that. No, when you are just having one function and one domain. Now, the example for this is similar to what we're doing. I can just say that evaluate the limit as x approaches 2 of x squared plus 7, and I want the 10th root of that. So this limit is simply saying that take the 10th root of the limit as x approaches 2 of x squared plus 7, and you know that I'm still gonna have the 10th root, and I take this 2. If I can plug it there, I will get 2 squared, which is 4 plus 7. So this nice thing is going to be just equal to the 10th root of 11. Of course, you cannot move past that. This is the final answer unless you want to plug it in a calculator. Let's look now at the last rule here, which is just saying that this is rule number 9. The limit as x approaches a of a constant is just constant. So you're just getting the same constant here. And if let's say you take the limit as x approaches a of x is just a. That's what this is saying. So If let's say someone is saying find the limit as x approaches 10 of 2, you know that the limit of a constant is just that constant. That's simple as it is. And let's say if someone is saying find the limit as x approaches 10 of x, you know that I just have to take this and plug it in, and I'm gonna get a 10. That's how easy these limits are. I am going to stop here, and next time, or in the next lesson, we will be talking about the squeeze theorem. Basically speaking, the squeeze theorem wants you to have two functions that are bounding the given function, and both of these two functions are actually having the same limit, so that the function in the middle is squeezed to the same value, because the value between two real numbers that are actually having the same value is just the same real number. That's what the squeeze theorem is all about, but we will talk about it in the next lesson. So just a quick example on how these rules are actually used beside the normal way that I've been showing you here. I want to look at our last tutorial here, but I'm going to do this like this. I want a new window, and then I'm gonna place it here, and then I'm going to anoint a file. I'm looking at tutorial 6 here. Not this one. I'm looking at tutorial 6. Anoint. No. Where's this? New window. What I'm actually looking at here is I wanted to find anoint. Where's tutorial 6 here? This is tutorial 6. Open. Yes. Now if you look at these problems here, I am actually going to look at only number 1. I'm not going to go further and look at all these other ones. You can try and use these, deal with these problems one by one. There's so many of these problems. If you're still interested, you can pause the video here and solve these problems by yourself. But here, what I want us to talk about here is this part here, which is this part here. Let me do this. I want an option here. I want to use this pencil so you can see. So here, if you have this nice thing here, I'm gonna use this part, this one. The limit as x approaches 2 of f of x is 4. The limit as x approaches 2 of g of x is minus 2. The limit as x approaches 2 of h of x is equal to 2. Is equal to 0, I mean. Evaluate the following limits if they exist. If the limit does not exist, explain why. So if you look into this here, we said that as long as the limit as x approaches 2 of that exists and the limit of this part exists, we can always evaluate this limit as going to be the limit as x approaches 2. I'm going to split this as one function and this one as one function. It's going to be the same as the limit of f of x. I have a plus here, so it's going to be a plus the limit as x approaches 2 of 5 times g of x, so 5 times g of x, right? Now I still have the limit as x approaches 2 of f of x plus, if I have a remember when we were doing this, that if I have a constant can always be pulled in front of the limit, so I can have a 5 here times the limit as x approaches 2 of g of x. Now going back to these conditions here, the limit as x approaches 2 of f of x is equal to 4, so I have a 4 plus 5 times the limit as x approaches 2 of g of x is minus 2 times minus 2, so this is going to be 4 minus 10, or just minus 6. That's how easy this thing is. And if you look here, the limit as x approaches 2 of g of x raised to 3, I can take the limit first and just say I'm going to have the limit as x approaches 2 of g of x, and then I raise it to 3. And if you look into this here inside, it is the same as the limit as x approaches 2 of g of x is minus 2. So I'll end up having a minus 2 raised to 3, which is the same as minus 8. So it's going to be minus 2 times minus 2 is going to be 4. 4 times minus 2 is going to be minus 8. And then the same thing here, that if I have a root, I can first take the limit and then take the root later. So this is going to be the root equal to the root of the limit as x approaches 2 of f of x. And I know that the limit as x approaches 2 of f of x is 4. So I will have a 4 inside here. And you know that the square root of a number, as long as the square root can be taken, is always going to be a positive number 2. So we're going to have a 2 here. If you look into this one here, it's going to be the same as the limit. Whenever you have a fraction here, take note that the limit of the denominator here is not a 0, so it's a number. So I can take the limit of the numerator and the limit of the denominator. So here we actually have the limit as x approaches 2 of 3 times f of x divided by the limit as x approaches 2 of g of x. Of course, if you have a constant in front of a function, you can always pull it in front. So I'll end up having 3 times the limit as x approaches 2 of f of x, and then divide here by the limit as x approaches 2 of g of x. I know this value here, so I will end up having 3 times limit as x approaches 2 of f of x. It was given as 4, so you have a 4 divided by, and then here it was a minus 2. I have a minus 2, so this is going to be minus, because positive divided by negative is negative. 3 times 4 is 12. 12 divided by 2 is actually 6. So we end up having that nice thing here. Let's look now at this one here, number 5. Before we do number 5, I want us to look at number 6. Deal with it, and then after number 6, we go to number 5. After number 5, we call it a day. So here, this is going to be equal to, I'm going to take the numerator alone and then take the limit of the numerator as x approaches 2 of g of x times h of x. And then I'm going to divide this by the limit as x approaches 2 of f of x. If I'm going a little bit down here, you will notice that I have multiplication of 2 functions. So if I have multiplication of 2 functions, and for me, when I'm taking the limit of each of these, I get a number, or let me say the limit exists, right? The limit exists of this one, and that one as x approaches 2. Then I can split the limit and say, I want the limit as x approaches 2 of g of x multiplied by the limit as x approaches 2 of h of x. This whole thing divided by the limit as x approaches 2 of f of x. Going back to the statement, we know that the limit of g of x as x approaches 2 is going to be minus 2. And the limit as x approaches 2 of h of x, it was a 0. And the limit as x approaches 2 of f of x, it was a 4. Just to confirm here, the limit as x approaches 2 of h of x is 0. I gave you a 0 here. The limit as x approaches 2 of g of x is minus 2. I gave you a minus 2. And then the limit as x approaches 2 of f of x, we have a 4. And then minus 2 times 0 is going to be 0 over a 4, which is just 0. So the answer that is actually expected in number 6, we're supposed to end up having a limit as x approaches a 0. Right. Let's talk about number 5 now. I want us to look at the limit as x approaches 2 of g of x divided by h of x. Now, if let's say here we're going to split the limit as x approaches 2 of g of x. Suppose we did this and we ended up with the limit as x approaches 2 of h of x. Now the issue here is that the limit is 0, so we cannot use that. We cannot use this because this one now end up becoming a 0, which is we don't want it. We don't want this to be equal to a 0. So using this, we cannot move from here to there. And secondly, if let's say we have the information that is saying that the limit as we're getting closer to 2 of this function, the limit is actually getting a 0. This is what can actually be happening. You might be having a function where x is equal to 2 here, and the function is like this. It's coming down at 2 and then it's going all the way up. So in this particular case here, whenever we have this limit of ours here, we can actually say that in this particular case, we'll end up having a nice conclusion on this, and we say that we end up having, because this one, as we're getting closer and closer and closer to 0, the answer is still positive. On the left, getting closer to 2, where the function is getting closer and closer to 0, but still positive. When you're on the left of 2, the answer is getting closer and closer to 0, but still positive. So the denominator would always be positive, and then our limit will take a negative infinity. Right. And if let's say we ended up having a different case whereby now we were saying that we ended up having a function of this kind, if we knew some information about h of x, we would see that the function is getting closer and closer and closer to 0 on the left of 2, but it is still negative. Once you go on the left of 2 is negative, and also here the output is still negative. So we would end up having this whole thing going to positive infinity, because the limit of this is actually negative. So when you're getting another negative here, we get a positive. So this function will be going to positive infinity. Right. But in the other case, when it was like this, we were going to get a negative infinity, because this one is already telling you about its negativity. Now, those are two scenarios, but we don't know what this function looks like. And then secondly, if I were to give you a function that is passing through 2 like this, right? This function here, as I'm getting closer and closer to 2, you will find out that if I get closer to 2 here, I get a value that is close to 0, but it's negative. So this whole thing here will end up actually having, I have a negative, but it's close to 0, so I will end up having a negative or a negative, a positive. So I will be going to positive infinity when I'm on the left of 2. But when I'm picking a value on the right of 2 here, you will find out actually that that value is positive, close to 0, but it's still positive. So I'm having a negative over a positive, which means a negative. So I will end up having at 2, the left will end up being positive infinity, and then on the right of 2 I will end up having a negative infinity. This and that is not the same. So if h is a function that is like this limit would not actually exist. So given this information and that information, and knowing only this information about h of x, we cannot actually conclude what is the value of this function, if it exists or not. We can't conclude. We were going to be able to conclude if we knew something about h of x, because you know what we do. We plot a curve, and then at x is equal to 2, a vertical asymptote, and then we deal with that. You know how to deal with it, but we don't have enough information to conclude which of the cases that I have talked about here will actually give us a value here. So if someone is saying that this limit diverges, It's literally because we don't know which of these cases are we actually belonging in. Right. The same thing when someone is saying that I want you to evaluate the limit as x approaches 0 of sine of 1 over x. Now, if I were to plug in a 0 here, I will end up getting a very so close to 0 on the right. I will get a very big number here, but that big number, I don't know whether it's placing me on positive 1 or negative 1 or on a value in between. That is why most people say that this limit diverges, because we don't know the output there. We don't know whether we're under negative, positive, or in between. The same thing in this case. We don't know which case are we falling on. So someone might say that this limit diverges. They are not wrong. They are just saying there are many possible solutions that can actually come out of this if we only have this information here. So in a nutshell, one conclusion would be this one diverges. You can say that this limit diverges. That's actually correct because there are so many possibilities. And then secondly, someone might say that we cannot really conclude about this because actually there are so many possibilities that can come out of this, but now we don't have more information about H. That's also correct on its own kind. So it depends now on who is actually dealing with your, who's actually your instructor. Is it someone who wants you to talk about diverging, or want you to say that actually I cannot conclude? That actually depends on the person, but I hope that you actually got the information around this, that actually by just having this, there are different possibilities that can happen depending on actually H. I will stop down there and then try and see if you can actually solve these problems and see if it will be possible for you to actually have a solution over this. Thank you for this particular lesson. Hopefully you got some insights on it, because on the next lesson we'll be talking about the squeeze theorem, which is one of the things that I can say that it's a little bit challenging when you have to choose functions, but the process is very easy. It's very easy. That's it.